solve 2025 physics honor question paper, that is modern physics. So in question 1, question A says what is the group velocity. We have to define what is the group velocity, then so that the group velocity of de Broglie wave is equal to the velocity of the particle. So let's see. So we have to equate them, that is the de Broglie group velocity is equal to the particle velocity. So in general, group velocity is defined as Vg is d omega by dk twice pi by lambda, and omega is the frequency. Okay, so in case of matter wave, we know that E equals to h cross omega and P equals to h cross k. So therefore E is nothing but p square divided by twice m. So omega, if we find omega, that is E divided by h cross. So if we replace E by p square by twice m, then we get these things. So that is h cross k square by twice m. So this is basically omega. And then differentiating omega with respect to k, we get that m by v. So m by v, so p by m. So p is the linear momentum, m times v. So therefore p by m is nothing but v. V is the velocity of the particle. So de Broglie group velocity is nothing but equal to the particle velocity. Okay. So the group velocity of the de Broglie wave is equal to the particle velocity. Proved. Okay. Next question given as to plot the energy density of a perfect black body as a function of wavelength for two different temperatures T1 and T2. Okay, we have to plot. So we know that the distribution function, that is basically energy density. Okay, so energy density is given as by this way. Okay, so where the curve T1 here given as for two temperature T1 and T2. If we consider T1 is greater than T2, then the curve for T1 is higher. Okay, the peak shifts shorter wavelength. So if we plot this u versus lambda, that is u lambda t versus lambda, so we get this type of plot. So this is for a particular temperature. Now from Wien's displacement law, we know that if the plot, this is the plot for temperature T1, then for a lambda max, lambda max and temperature T, it will be a constant value. It always gives constant value. So whenever T increases, that means there is a relation between lambda and T, so inversely proportional. So lambda max is proportional to 1 by T. Okay, that means if we increase temperature, then lambda max will be, decreases. Okay, so we get different lambda max here. Lambda max in the sense at which value of lambda u of lambda is maximum. Okay, so that is the lambda max. So lambda max shifted towards this origin for higher temperature. So the plot looks like, this is for T1 and this is for T2. This is the plot, T2 greater than T1 plot. Okay, so here lambda max is for higher temperature, lambda t. This multiplication must be, this product must be same for all plot. That is a constant value, Wien's constant. This is called Wien constant. Okay, so the peak shift shorter wavelength, so lambda max t equals to constant, that is the Wien's law, Wien displacement law. So draw two line curves. So this will be the plot. Okay. Next question. So that the momentum operator, that is P, is Hermitian for the class of a function which go to 0 at infinity. We know that the momentum operator, that is minus grad of that is iota h cross, sorry. So iota h cross grad in general minus iota h cross del x if we consider on coordinate along x-axis. So what will be the answer of C? So answer of C will be, so this is the momentum operator. Okay, so an Hermitian operator, suppose we are finding the we consider O cap is a Hermitian operator, and we are finding the expectation of this operator. You can write this way: expectation, that is psi 1 O cap psi 2. Okay, so we find this form and get this thing. So for it is a square integral function, it is vanishing for x tends to plus minus infinity, and substitute the value of P here. Okay, so here we substitute the value of O cap is nothing but the at operator, that momentum operator. We substitute the value here. So P cap, instead of O cap we put here P cap. So P cap is nothing but iota h cross del x. So after substituting this, we get the this expression of I, and if we integrate this, then it is nothing but so it is nothing but minus iota h cross minus infinity to plus infinity psi 1 star. Okay, and then d psi 2 dx and then dx. Okay, so then it again iota h cross del iota h cross minus infinity plus infinity, so it becomes d dx of, we can write it as I think we can write this as psi 1 star psi 2 and then d dx. Okay, this is the first part, and second part we can write minus iota h cross minus infinity to plus infinity. So if you consider this, then we have to subtract this part, that is d psi 1 star dx into psi 2 dx. We have to subtract this term. Okay, so this is nothing but d dx is cancelled out, so d of something, so integration dx is nothing but x, and limit minus infinity to infinity this term, and the remaining term is this. So we have to this is nothing but like this, d dx of psi 1 star psi 2, that is basically d psi 1 dx and psi 2, then plus psi 1 star d psi 2 dx. So we basically we replace this with the help of this form. So there will be a negative sign, and this negative positive, so you get this term. So integral value will be this. Now if we put the limit here, okay, so at plus minus infinity, at x tends to plus minus infinity, at x tends to plus minus infinity, both psi 1 and psi 2 are vanishes. Okay, all vanishes. So if all vanishes, then this term contribution of this term will be 0. Okay, only we get we have only this term, that is I will be iota h cross integration minus infinity to plus infinity del psi 1 star dx psi 2 dx. Okay, then if we integrate this, that means we can rewrite this form with the help of this form, that is iota h cross del psi 1 del x star. If we take star, then it will be conjugate, that means minus iota h cross and d dx operator is not Hermitian operator at all. There is a negative sign also, so that is minus dx and then psi 1 star. So it will, this minus and minus become plus, so we get this term as a whole. Okay, so after small rearrangement is taken place here, and after that we get this form, that is p psi 1 star psi 2. So this implies that p is a Hermitian. Okay, Hermitian of this function space. That means this is the general form of O cap is called Hermitian. Okay, so if O cap is a Hermitian operator, then it must follow this form. Okay, it must follow this mathematical form. Okay, so here we can see that the p momentum operator uh, follows same things here. Okay, that means momentum operator is a Hermitian on this function space. Okay, so this is the general form, we have to remind it. Okay, in general form for Hermitian, a function or a operator is called Hermitian if and only if it follow this relation, that is psi 1 star O cap psi 2 dx equals to minus infinity to plus infinity O cap psi 1 whole star then psi 2 dx. So here the momentum operator satisfies this equation, that's why it is called Hermitian. Okay, now next problem. Next, so problem D. So a particle having mass m, wave function given as a psi of xt. So very easy problem, that is e to the power minus a times mx square divided by h plus I iota t, I think. Okay, so a is the normalizing constant, a is a small a positive real constant, and we have to find this a. So to find this constant we have to normalize first. Okay, so question number D. So function is given by this way, that is a is a constant term, then exponential of minus amx square by h plus iota t. Here given a is positive, a is a positive quantity. So it is a obviously we can see the wave function is a time dependent function. Okay, so the wave function is a time dependent function. So if we taking the squared, that means psi star psi is nothing but magnitude of psi squared. So we can take the magnitude of this. So if we take magnitude, then there is a real part and there is a imaginary part. If we break this part, then we get e to the power iota a mx square by there is no iota, so it will be e to the power minus a mx square by h cross. This is the first term, first part of this exponential, and last part is e to the power minus iota at. So if we take the conjugate of this, then it will be e to the power plus iota at, and then after taking the product of this psi star psi, then this imaginary part vanishes. Okay, then we get simple, the mod of psi square is nothing but this, then we have to integrate this. Okay, so we have to integrate in minus infinity to plus infinity interval. After integrating it, we easily get the answer. So this is the general form of the gamma function. So here beta is there, root under pi by beta, where beta is a twice am by h cross. So using this beta function, gamma function, we can get the answer. So here the normalizing condition is twice a m divided by pi h cross to the power 1/4. Okay, so this is the answer. Now next question E, I think. Okay, question E. The function of a particle at time t equals to 0 is given as psi of x0. Okay, so this is time independent wave function is given. So here x is positive and a is a constant. So find its momentum space. So at t equals to 0, okay, at t equals to 0 we have to find the wave function in momentum space. That means we have to take the Fourier transform of the given wave function, position space to momentum space. Okay, to convert the moment wave function in position space to momentum space, we have to take Fourier transform of this wave function, which is in real space or real configuration space. Okay, so then let's go to the answer, question E. So at t equals to 0, wave function is given in x space, in real space, that is 2 divided by a to the power 3 by 2 x times e to the power minus x by a. And if we use the that is called the Fourier transform, so if we use this form, that is 1 divided by root over 2 pi h cross root under. So Fourier transform যেটা ইউজ এখানে করা হচ্ছে যে f of omega যে ফর্মটা ইউজ হচ্ছে, so 1 divided by root under twice pi h cross minus infinity to plus infinity f of x function, then e to the power minus iota omega x, okay, into dx. So this is the form of Fourier transform. 1 divided by, if we put constant part in front of the integration, you can put you can ignore this term also. Okay, so if you remove this term from this transformation, then you have to consider this term for reverse transformation, reverse Fourier transformation. Okay, now, so this is in omega space, that means in k space, and this is in f of x in configuration space. So e to the power minus iota omega x dx. So this is the general form. So we implement this form. So we directly use here p, that is in momentum space. So phi of p equals to 1 divided by root over twice pi. So since it is p, in case of omega there is only root over twice pi, there is no h cross here. Okay, if we use here, if we use p here, then it will be root under twice by h cross. Okay, so 1 divided by root over twice by h cross minus infinity plus infinity, then substituting this value psi of x0. So psi of x0 is this, and the remaining part as it is, e to the power minus iota px by h cross, then dx. Okay, then if we rearrange this term, this exponential term, then it will be e to the power minus x is common, so 1 divided by a plus iota p by, okay, iota p by h cross. Okay, now substitute this term by another variable 1 by a plus iota p by h cross. We consider this as a gamma. Okay, so substitute this term x, this term is a constant as it is, we can take out of this integration, and we there is another thing, the minus infinity to plus infinity, the integration becomes 0 to infinity because of okay, e to the power minus px, we can take it as 0 to infinity because there is, I think, if this function is even function, then we can take it as a 0 to infinity, but why it is taken 0 to infinity? So the wave function is defined okay, so the wave function is defined in the positive x region. Okay, there is no wave function, that means there is no contribution of this wave function in negative x region. So when x is less than 0, then the wave function is 0. Okay, basically, so the wave function is defined in positive x region, that's why we take here 0 to infinity integration. Okay. So what we get, 0 to infinity x e to the power minus gamma x dx. So if we use here gamma function, then we get this value 1 divided by lambda 1 divided by gamma square. Okay, so therefore what will be the gamma phi p? Now phi p will be 1 divided by this part and this 2 divided by, as it is, constant term, then substitute this constant this integration value here 1 by gamma square. So we take the gamma as 1 by a plus iota p by h cross. After substituting this, we get this form. Okay, then rearranging after rearranging this, we get the wave function in momentum space. Okay, so this is the general form of wave function in momentum space. Okay, done. Next question is F. Question number F. So question number F is given as, so find the constant b which makes e to the power minus, I think it is alpha x now. So e to the power minus alpha x, so it is an Gaussian function, an eigenfunction of an operator this. Okay, that means if this function is an eigenfunction of this operator, then what will be the value of b? Okay, so we have to calculate b. What is the value of b, so that this function is an eigenfunction of this operator? Very easy. Okay, so the operator is given as d2 dx2 minus dx square. Okay, now our function is basically e to the power minus alpha x square. So we have to show that this operator is a eigenfunction of this, this wave function is an eigenfunction of this operator. Okay, so psi of x is this. So if we differentiating this, then we get okay, we can directly operate this on this wave function. Okay, we can directly operate this operator on this. So d2 dx2 minus bx square on psi, so then it becomes d2 psi dx2 minus bx square psi. So now d2 dx2 of psi, that means we have to perform second order derivative of x with respect to x on psi. Okay, so after taking the second order derivative, after the first order derivative, it becomes minus twice alpha x, then e to the power minus alpha x square. After taking the second order derivative, so for second order derivative, e to the power minus alpha x square is taken as it is, derivative of x, it gives minus twice alpha. Okay, and after that x is taken as it is, x is as it is, and after that derivative of e to the power minus alpha x square, that gives minus twice alpha x again. So it will be 4 alpha square x square, then common e to the power minus alpha x square. Okay, so this is the second order derivative. So if we substitute here and then common out the term psi, so to prove this function, this psi function is an eigen function of this operator, then we have to arrange this like this equation. We have to arrange this. That means if we operate a on psi, it gives lambda psi, then this equation is called the eigenvalue equation. And if we get again psi after operating a on psi, then it is called eigenfunction. Okay, so then psi is called the eigenfunction, then a lambda is called the eigenvalue, and this equation is called eigenvalue equation. Okay, so then we have to equate to I think if we equate this term with 0, then we get the solution, because x is a variable here. Okay, psi depends on x, So if we uh, leave this term x, then it does not make the eigenvalue equation. Okay, to make this eigenvalue equation we have to equate this term, I mean we have to vanish this term, we have to remove this term. So to remove this term, this 4 alpha square minus b term must be equal to 0. That means 4 alpha square minus b will be 0. Then from here we get the b value. B is nothing but 4 alpha square. Okay, so b is nothing but 4 alpha square. This is the exact value of b. And if we're talking about what is the eigenvalue, then the eigenvalue will be d2 dx2 minus bx square operate on psi is it gives minus twice alpha into psi of x. So here this minus 2 alpha is the eigenvalue of this operator, and b will be 4 alpha square, so that it can follow the eigenvalue equation. Okay, next one is question G. Let's see what is the question. So question G, so that if psi be an eigenfunction of the operator A with eigenvalue lambda, that means A operate on psi, it gives lambda psi. Okay, so then it is also eigenfunction of e to the power A with the eigenvalue e to the power lambda. Very interesting question. Okay, so we can solve it. So it is given that A is a eigenfunction of psi and eigenvalue is lambda, so basically A psi gives lambda psi. Okay, so if we consider the exponential form e to the power A, so in general e to the power x, what will be the expansion, series expansion of this e to the power x? This is nothing but 1 plus x square by 2 factorial plus x cube by 3 factorial. Okay, like this. Okay, that means summation n equals to 0 to infinity. Okay, then x to the power n divided by n factorial. Okay, but in case of operator form, if we consider x as an operator, like x equals to a cap, then the form will be e to the power a cap equals to summation n equals to 0 to infinity this is a cap to the power n divided by n factorial. Okay, this is the form of exponential. So if we operate this operator on psi, so what will be the form? So this form looks like this. So if we operate in a on psi, it gives lambda psi. If we operate again a on this form, that is a of a psi, then it gives a lambda psi. It will be lambda square psi. So a, if a operate on psi 2 times, if a operate on psi by 2 times, then it gives the eigenvalues lambda square. Okay, it gives the eigenvalues lambda square. That means if a operate on psi by n times, if a operate on psi n times, then it gives the eigenvalue lambda to the power n. Okay, lambda to the power n. We consider, we take here that form, that is lambda to the power n psi. Okay, so after that this will be the, that is lambda to the power n divided by n factorial. This will be the eigenvalue. Okay, so what will be the eigenvalue? Eigenvalue will be e to the power lambda. Okay, very interesting problem. So psi is eigenfunction of e to the power a with eigenvalue e to the power lambda. Okay, next one, prove by induction. Acha. Okay, induction method method, with the help of induction method, we have to solve this. That is, we know that xp there does not commute, so it gives iota h cross. We have to prove this with the help of induction method. So we initially know that the commutator of x and px is nothing but iota h cross. Now we initial step we assume that the equation holds. Okay, this relation holds, this relation is exist. Okay, that is x to the power n px commutation relation gives us iota n h cross x to the power n minus 1. Okay, now here we consider x to the power, we have to here we calculate x to the power n plus 1 px. Okay, we have to calculate this commutation value, commutator value. Then if we use this relation, that is nothing but x to the power n into x, then we use this commutation rule, then you get x into a commutation of x to the power n px plus commutation of x and px, then x to the power n. We replace this x px is nothing but iota h cross, and x to the power n px, we assume that this equation holds. That's why we put that value, and we arrive this form, that is x to the power n plus 1 px is nothing but iota into n plus 1 h cross x to the power n. So this is for n plus 1. So if we replace n equals to n minus 1, then it gives basically x to the power n px is nothing but iota n h cross x to the power n minus 1. That means we get the answer. Okay, so this is the way of solving this type of problem with the help of induction method. In induction method, we in initial step we assume that equation is correct. This type of equation holds, and we take this form x to the power n plus 1. We find the commutator value of x to the power n plus 1 with respect to p, and after getting the result, we reduce this n, we reduce this power n plus 1, we reduce by 1 unit, that means n minus 1 plus 1, that is n. So that's why it is called the induction method. Okay.